Okay, we looked at the radius of an atom. How about the radius of an ion? It decreases down a group for the same reason. More energy levels and shielding. But now, we can't compare anything. We're going to compare cations to cations. Remember, cations are positive. And we're going to compare anions to anions. Anions are negative. So, within the cations, we decrease across the period because of more nuclear charge. But cations are smaller than the atoms, and anions are larger than the atoms. So, which particle is larger? Magnesium, because we lose electrons, it's going to get smaller. Negative ion is going to be bigger. Now when we're comparing phosphide and nitride ions, it's going to be bigger because of more energy levels. When we compare aluminum and indium ions, indium is going to be bigger because of more energy levels. Now, ionization energy. The energy required to remove one electron. It increases for each electron removed. This is important for metals because they lose electrons to form ions. Now, the ionization energy decreases when you go down a group and increases when you go across a period. Notice it's the inverse of size because if your electron is farther from the nucleus isn't holding it very tightly. So which has a lower ionization energy? We're looking at sodium and magnesium. Sodium would have a lower ionization energy. Ionization energy increases that way, increases that way. Look at K and Cu. K would have a lower ionization energy. Less valence electrons. Typically lower ionization energy. Looking at lithium and cesium. Cesium would have a lower ionization energy. The valence electrons are farther from the nucleus. And if we look at aluminum and silicon, it would be aluminum. Now, electron affinity is the energy change that accompanies the addition of an electron to an atom. So this is important for nonmetals because they gain electrons. Just like with thermodynamics, we have our same sign conventions for energy. Energy released is a negative. Energy added is positive. It becomes more positive when we move down a group, but there's only small differences. It becomes more negative as you move across a period. Okay. And becomes more negative as you move across a period. That makes sense because you're moving from metals two nonmetals. Nonmetals want to gain electrons. So fluorine would have a greater electron affinity because it's smaller. Its valence electrons are already closer to the nucleus, so it can pull in more electrons. Chlorine would have a greater electron affinity than sodium. We would expect a positive electron affinity from a noble gas, already full. Doesn't want more electrons. We would expect negative from bromine because it only needs one electron for a full level. We would expect a negative for oxygen because it only needs two electrons for a full level. And the last trend we're going to talk about is electronegativity, which is the tendency of an element to attract electrons in a bond. Going to be important for nonmetals in covalent bonds where they share electrons. And notice it has the same pattern as ionization energy, which is the opposite of size. Small atom attracts electrons well. A large one doesn't. And now, you remember that fluorine is the most electronegative element, you can pretty much remember the pattern. Okay. So we have fluorine here, the most electronegative element. So electronegativity increases as you move towards fluorine. Noble gases are full, so they don't want to attract any electrons, and they rarely bond. So, which is more electronegative? We would have oxygen, we would have nitrogen, we would have oxygen, and of course we would have fluorine.